Okay, alright, there are no questions. We'll move on to the next one. Module on. Okay. Okay. So here we'll talk about, we'll try and understand a little bit more about what are matrix inverses, and what does the matrix inverse mean, and then look at generalized inverses for not just square matrices, but for fat or rectangular matrices, and for matrices that have that are not full rank. Okay. See, before we do that, right? Okay. Let's say this is R2. Let's say we've chosen this as the origin, and I have a vector B, okay, which corresponds to this point. Okay, assuming that this is the origin. Okay. Now, usually, I can just show you that the vector B represents this point, right? That the point is in a fixed location in space. Okay. But the moment I want to represent this using a number, right? Then it turns out you need to have reference. For example, if you're talking about the mass of my body, right? My mass is an inherent property of my body. It's some quantity that exists, right? But the moment you want to express it in terms of a number to convey how much my mass is, then you have to have a reference. You either use pounds, kilograms, grams, milligrams, whatever is your choice. That means you need to have a reference to express it in a number. Depending on what reference you use, the exact number that is used to represent the weight of mass of my body is different. Right? The same thing applies for vectors as well. Right? This vector B represents this point. Right? That point exists in some location in space. But the moment you say I want to represent this point or this vector by a set of numbers, then you need to have a reference. And that reference in the case of vectors is simply what we call a basis. Okay. What we might do is we might draw two lines like this, and then we'll find out this distance, and then we'll call this B1, call this B2, and then we say, okay, I can now represent B1, B2. Okay. Now, if I give you these two numbers, the only way for you to know the exact location that I'm talking about is if you also knew what was my basis. In this case, I've inherently chosen vectors along this direction and this direction as forming the basis for representing my vector B. Okay. So in this case, we had a vector, say A1, A2, and we had a basis A1, A2. So these numbers that I've written down for this vector, in fact, I should not say these numbers represent this vector B. I should be a little bit more specific. These numbers represent this vector B with respect to this basis. Right? Because if I chose a different basis, right? Let's say I had, I don't know, C1 and C2. These two form a linearly independent set. Their span is R2. That means C1 and C2, the set C1 and C2 forms a basis for R2. Right? I can find a representation for B in terms of these, right? And these might come out, these might have different values. BC1. Okay. These won't be the same as this. Okay. And we know how to find this geometrically. The representation of B in terms of this basis, C basis, is you simply extend these lines, draw parallel lines from the tip of B along this direction and this direction, and wherever they meet these two subspaces, you know you have to take so much of C2, so much of C1, and then the sum of those two will give you, and those, how much of C1 and C2 you take is given by BC1 and BC2. And this is the representation of B in the C basis. Okay. Okay? So the bottom line is, the vector is a vector and that exists on its own. But the moment you want to represent using numbers, representation using numbers always require a basis or a reference. Okay, and your numbers will make sense to me, or you can convey information about a vector correctly to me only if I know what the basis is. Okay. See, so far, whenever we talk about a vector, right, I would simply say, okay, x equals, right? And the moment I write numbers for a vector, you should ask me what basis. Okay. So far, we've not made any explicit mention of what the basis is, because whenever no mention is made, assume it's in the standard basis. Okay. If I don't tell you anything about a vector and I simply write down numbers, we assume that it's in the standard basis. Okay. If I am to write x in the C basis, for example, right, then I have to explicitly tell you that the representation of x in the C basis is 2 minus 1, 3. If I don't say, then you will get, and if you assume that this was the representation in the standard basis, then you have the completely wrong information about x. Okay? Alright. Now if that is the case, right? If we had B and we had the vectors C1 and C2, and I asked you what is the representation of B in terms of C1 and C2, geometrically you know how to find out. Okay? How do we do it algebraically? Okay? Let's say we have a basis A. We're talking about vectors from Rn or R, let's say Rp. Let's say we have a basis for Rp. Okay, how many vectors will that set have if I have a basis for Rp? 3 vectors. Okay, A1, A2. Okay, I call this the A basis, and this forms this is a basis for Rp. Okay. Let's say I write down numbers for these again. I write down some numbers. Okay. I don't mention anything. For now, assume that each of these vectors now, for which I've represented using numbers, these are all represented in the standard basis. Each of these vectors themselves. Okay. These form a basis for Rp, but each of those elements are represented in the standard basis. Okay. And then let's say I have another vector B, for which also I've written down some numbers. Okay. And this is also in the standard basis. Okay. B is the representation of this vector that I am interested in the standard basis. Now what I would like to know is, I'm not interested in the standard basis, even though that is the information I have at hand. How do I find the representation of B in the A basis if I have its representation in the standard basis? Is the question clear? No? Okay. Here. I have some vector like this. You assume the origin. Okay. We've chosen an origin, and then we've chosen these two directions to be the directions for the standard basis. Okay. The standard basis is an orthonormal basis. Okay. If I tell you the representation of a vector B in the standard basis is 2, 1, where would you draw it? Where would you draw it? Sorry? Sorry? No, exactly where? Here, 2 units in this direction, 1 unit in this direction, because the standard basis, the basis vectors have length 1. And what this means is you take 2 times of E1 plus 2 times of E2. Sorry, one amount of E2, right? That would mean a vector like this. Okay. So, if all of us agree that we're only going to be working in the standard basis, then if I give you these 2 numbers, you know exactly what point I'm talking about or what vector I'm talking about. Okay, fine. So that's clear. But let's say for some reason we don't like the standard basis, we are forced to use some other basis, let's say some A basis. Okay. In that case, the A basis vectors are not, let's say, this is A1, this is A2. Okay. Now, I have these 2, right? I'm going to call this P. Let's say I have these 2 vectors and I have their representation in the standard basis. Maybe I have not drawn it properly. Let's say it's 1, 2, and let's say 1 minus 1. These are the representations of A1 and A2 in the standard basis. Okay. Given all this, I want to know what is the representation of B in terms of A1 and A2. Okay. Okay. Or what is the representation of B in the A basis? That means I'm looking at B. For now, assume if I write a subscript following a vector, this subscript means the basis in which that vector is represented. So I'm looking for 2 numbers, BA1, BA2, such that if I take BA1 times the first vector of the A basis plus BA2 times the second vector of the A basis, I get my original vector B in the standard basis back. Okay. So I need to find out these 2 given that I know A1, A2 and B. Okay. But we've seen stuff like this before, right? You can express this like this. If you form a matrix like this, where the columns are the basis vectors, and then you multiply it by some other vector, BA1, BA2. This thing can be expressed like this. You're interested in solving this equation. Solving this equation is equivalent to solving this equation, right? Because this is just a matrix notation of this. That means what we are essentially talking about is solving a problem like this: A into BA equals B. Essentially, Ax equals B. Right? So, this question of going from some basis, a representation in some basis, to a representation in another basis is essentially a problem of solving a set of linear equations. Okay? And that also tells us what an inverse really means. Right? So, the way you would solve this in principle is your BA, which is the representation of B in the A basis, is simply A inverse B. Okay, I can take the inverse because A is full rank. A is full rank because the columns of A form a basis for RP. Okay, if it forms a basis for RP, that means they are a linearly independent set. That means the rank of A is P. Rank of A is P. That means inverse exists. It means this is allowed. Okay, and this tells us what is an interpretation for the inverse of a square, full rank square matrix. The A inverse is simply a matrix that allows us to change basis. Okay. Because if you take A inverse, right? If you if you post multiply A inverse by a vector represented in the standard basis, what you get out is the representation of the same vector in the A basis. Okay, and the A basis are simply the columns of A. Okay, and that is exactly what, or at least geometrically, that's what an A inverse means. It's a matrix that allows you to change basis. Is that clear? Okay. If that is the case, you tell me what would be the given that this is A1, A2 and B, all of them are in the standard basis. In this particular case, what is BA? That means you will have to write down the set of linear equations, find out A inverse. If you don't know how to find A inverse, just solve those two linear equations using any method that you know, and then you tell me what the representation of BA or representation of B is in the A basis. What would be the set of equations that you get for these three, for A1, A2, B, in terms of BA1 and BA2? Well, it will be BA1, 1, 2 plus BA2, 1 minus 1 will be equal to 2, 1. You'll get two set of equations and then solve for it and tell me what this is. It's 1, 1? It might be, I don't know. Just verify that that is correct. Yeah, it's right. If you add these two, you get 2. If you add these two, you get 1. That's fine. 1, 1. Yes. So the representation of B in the A basis is 1, 1. If you were working with the standard basis E1, E2, the representation was 2, 1. That means you take 2 times of E1 and 1 times E2 and you add them together and you get this point. If you're working in the A basis, you take 1 times of A1, 1 times of A2, and then you get B. Okay? Alright. Now, this whole process becomes a lot more simpler if A was orthogonal. Or if A is orthogonal, then A inverse is A transpose. Okay. If A is orthogonal, the columns of A form an orthonormal basis for whatever space this is from. Let's say if this is R P cross P, then the columns of A form an orthonormal basis for RP. Right? If you have an orthonormal basis, we know how to find the representation in an orthonormal basis, right? This is from the very first lecture. In fact, we said that is why orthonormal bases are special. Do you remember? How do you find the representation? So, in this case, if A1, A2 was in fact an orthonormal basis for R2, how would we find BA1 and BA2? There is a very simple formula. What is it? Do you remember? It's simply A1 transpose B, A2 transpose B. Okay? And in fact, because A is orthonormal, A inverse is A transpose. If you do the matrix multiplication, you will find that this is in fact this. Because A is A1, A2. What is A transpose? What is the transpose of a block matrix? This is a block row. That means you'll have a block column. That means you have 2 columns. You'll have rows here. What will be those rows? It will be transposes of the individual elements. if you multiply this by a vector B, the two elements that you'll get is A1 transpose B, A2 transpose B. That's exactly what it is. Alright, okay. That's the interpretation of A inverse. Okay? One way to look at what A inverse really means. In fact, there are lots of other interesting things that you can find out about the relationship between the columns of A and rows of B and so on and so forth. Maybe I won't get into those this time because we don't have a lot of time. I'll skip that. For now, I think it's enough if you just know this for sure. Okay, right. So that's about square matrices. Now, so far we've only looked at inverses for square matrices, and when we have square full rank matrix, then we said A is a square full rank matrix. Then we said there is a unique inverse such that if you multiply it on the left or if you multiply it on the right, both of them will be equal and both of them will give you I. Okay. So now we'll assume. Okay. We had to explicitly talk about being able to pre-multiply and post-multiply because matrix multiplication is in general not commutative, and also because if this is not satisfied, right? Let's assume the full rank condition is still satisfied. Okay. But if the matrix is not square, it turns out, so now let's say A belongs to P cross Q, but full rank. Okay. That means rank is the minimum of the number of rows or columns. Then you have a situation like this. Then you have either a matrix like this or a matrix like this. When you have rectangular matrices like this, it turns out you do not have a inverse in the sense that like this, when you have a square matrix. You have an inverse, if you pre-multiply or post-multiply, you get an identity matrix. Right? But it turns out if you have a tall or a fat matrix, for a tall matrix, it turns out that you can find a fat matrix, which if you pre-multiply, okay, this will give you IQ. Okay. And if you have a fat matrix, you can find a tall matrix that you post multiply, so that you get, what would you get here, IP or IQ? This is A. Will this be IP or IQ? So this is P, this is Q, this is Q, this is P. No, sorry. Yeah, that's fine. Okay. So if you have tall matrices, these two are possible. Okay. And only these two are possible. So if you have a tall matrix, you cannot find a fat matrix. So what is not possible is this. If you have a tall matrix, what you cannot have is this. This is not possible. Okay, we won't worry about why that is, but for now just take it that that is not possible. Similarly, if you have a fat matrix, you cannot find a tall matrix that goes on this side, which you can pre-multiply such that you get an identity matrix. Okay, so the moment you move from square full rank to not square full rank or rectangular full rank, the first thing you lose is you don't have an inverse that you can pre or post multiply to get I. You can only have one. Okay, that's the first point to remember. Okay, you only have either a left inverse if you have a tall A, or you have a right inverse if you have a fat A. Okay. If it's square, then there is a right inverse and a left inverse, and both of them are equal. Okay. And in the square full rank case, A inverse, if you remember, was unique. Okay. There is only one matrix A inverse that will satisfy this. There is no other matrix that will satisfy this. Okay. And in fact, you lose that the moment you move to rectangular matrices. You only have left or right inverses, and two, they are not unique. Which basically means if you have a tall matrix, there are an infinite number of left inverses. If you have a fat matrix, there are an infinite number of right inverses. Okay. This again, the important thing is full rank. It has to be full rank. We will talk about the rank deficient matrices later on. Okay. That's the case. We'll now talk about left inverses. Okay. Only tall matrices have left inverses. Okay. Tall full rank matrices. Okay. And if you have a tall full rank matrix and you multiply it by, and we'll call it C, that's the left inverse, and this is your A, what you get when you multiply this is Q. Identity matrix of size Q. Let's look at the simplest possible. What is the simplest possible tall matrix in terms of shape? When Q is 1, it's simply a column. Okay. Let's say we have a this where AI, well, where A is P plus 1. Okay. It's full rank, that means A cannot be 0. Okay. The rank is 1. Now, can you think of a matrix C whose size will be, see, if A is of size P cross Q, and this will be Q cross P. That means, can we think of a C whose size is 1 cross P, such that if you pre-multiply A by C, you get IQ, Q is 1, so that means you get just 1. Okay. In fact, this is quite easy to find. Okay. If you simply form C as this matrix, you take A, you take its transpose. Okay. If C was just A transpose, right? It was A transpose, sorry. A transpose, then this product will be A transpose into A. This will simply be, this is nothing but the second norm of A square, some scalar, right? If this product is to come out as 1, if I simply divide this by if I form a matrix C like this, right, and this was divided by square, if I multiply these two, I get numerator and denominator are the same, you will in fact get 1. Okay. For the case of a column matrix, one of the left inverses is very easy to find. You simply take A transpose and then normalize its length. Well, you don't normalize it, you divide it by the square of the length of that vector. And this row matrix is the left inverse for A. Okay. Now, is that the only left inverse possible? When I said there are infinitely many left inverses, how do you find, or how would you now find the other possible left inverses? Well, one way to do that is, let's say you start with this, right? we know that if you take this C and you pre-multiply, or if you pre-multiply A by C, you get 1. Okay. Now, if I simply add to this row any row that is orthogonal to A, what will happen? Okay. So, if let's say I take this C, and let's say that is A transpose divided by, this is my original C. Okay. Now I form another row which I call C cap. Okay. And this is simply any vector that is perpendicular to A. Right? And if I add these two together, C plus C cap and A, well, if I can multiply it inside, so I get CA plus C cap A. I know this gives me 1 because I've chosen C to be this. Whereas here I have, now assume this is a row, okay? Maybe to be consistent, right? I won't write it like this. Okay, such that C tilde transpose into A is 0. That means C tilde is orthogonal to A. This product will always be 0, so this will disappear. Okay. Means now C is a left inverse. Any matrix C plus C cap is also a left inverse, because C cap is any vector that is orthogonal to A, and if I simply add any vector that is orthogonal to A to this C, I get all possible left inverses. So this is a demonstration of the left inverse for the simplest case of a column vector, okay, and the demonstration that there are infinitely many. Okay, let's do an example. Say we're talking about, okay, can you tell me a left inverse for this matrix? Tell me one left inverse. Call it C. What will be the left inverse? Well, you don't have to think too much, right? One possible left inverse is this. Simply convert that into a row divided by square of its length. That means this is a valid left inverse. If I take the product between these two, let me write it as A. If I take the product CA, I will get 1. Half plus half will give me 1. Can you tell me other possible left inverses? This is 1. Can you give me another possibility? In fact, more explicitly, let me write it like this. Sorry? Yeah, sure. Yes. How did you get it? C cap will be 0, is it? C cap cannot be 0, right? Because the sum of C cap is 0, sum of C cap with C is just C. Well, you simply, C cap is what? Any vector that is perpendicular to A, right? What are all the vectors that are perpendicular to this? Okay, so in fact, the general expression for C is half plus alpha, or so alpha can take on any value, right? This is in this case, this is the most general expression for the left inverse for A. Okay, and this alpha minus alpha did not come magically. It's simply alpha minus alpha is a set of all vectors that are perpendicular to A, because that will not affect. In fact, alpha minus alpha will essentially go to 0. That's why if you pre-multiply A by C, you still get 1. Okay? All right. All right. Okay. Now, that is the case. Now, we know that if you have a system of equation like this, A is full rank and square, we know we can solve this by, in principle, like this, right? Now, if you have a tall A, and full rank, okay. Now the question is, can we solve for this? Can we solve this set of equations for a tall A using this idea of a left inverse? Because for a square A that was full rank, we could use the inverse of the matrix to solve for X. The question is, can we use the left inverse to solve this? Okay. But before that, if you had an equation like this, what are all the possible solutions given that A is full rank and tall? Okay, if I had said yes to your answer, right, would you have changed your answer? No, okay, all right. Now, so I want you to think about what you're saying. It's tall. Okay, what are the conditions for the 3 possible solutions? The 3 possible solutions, right? Unique, no, infinitely many. When do you have no solution? Span of columns of A. Yes, okay, that's good. Now, what about unique or infinitely many solutions? Yes, okay. So I just told you that rank of A is rank A is full rank. That means it's equal to it's equal to the number of columns because this is a tall A. Now what are the possibilities? If you know that this is full rank, now what are the possibilities? I'm sure you know this. Maybe you're not just confident. Say it. It's okay if it's wrong. Yeah. Okay. Yeah, you're right. There are 2 possibilities only. There is a unique solution, or what? No, it's full rank, right? Or see, if it's full rank, there is no question of. Or let me put it this way. Sorry. I'm wrong. If the rank of the matrix is equal to rank of A equals P, okay, then you always have, hold on, I'm still confusing myself. Yeah, if the rank of A is Q, okay, then you have, when you don't have a situation of infinitely many solutions, then you only have unique or no solution, okay. Because the matrix is tall, full rank, that means the rank has to be Q. Because Q is less than P. And the rank is always the minimum of the 2 numbers. Okay, alright. So these are the only 2 possibilities. And the possibilities are when B is in the, I don't have to write span, I have to say column space of A, or not in the column space of A, B is in the column space. Those are the only 2 possibilities. Okay. It turns out that if B belongs to the column space of A, you take any left inverse, okay, and you pre-multiply both the left hand side and the right hand side by C. Let's say C is a left inverse, then CA into X will be C times P. Because C is a left inverse, this will be I, that means okay. You can use any left inverse to solve this, but here is the catch. Okay? This multiplication that I did had no relationship to whether B was in the column space of A or B was not in the column space of A. I could have done this for anything. Right? For example, if you do this, does this have a solution? Okay. Does this have a solution? Well, it does not. There is only one x here. That means what you can produce here is all the vectors that are scaled versions of 1, 1. This is not a scaled version of 1, 1. That means this cannot be solved. There is no x that will such that the left hand side is equal to the right hand side. But we know what is the left inverse for this, right? What is the left inverse? Well, it's half half, right? I could have taken half and here. Right? I'm allowed to do this. If I multiply by c, this disappears, right? So I get x equals half of 2 plus half of 3, which is that right? Yeah, it's 2.5. There, I've obtained a solution. The problem is this. Okay, now you take this x, okay, and then you find out a times x. What is a times x? If you chose x to be this value by simply taking some left inverse and multiplying it like this. Well, 2.5, 1, 1 into 2.5. The vector you get is 2.5. This is not equal to 2, 3. Okay, alright. So, the point is this. If Ax equals B is solvable, right? That means B is in the span of, is in the column space of A. Then you take any left inverse and pre-multiply by the left inverse. Then this is the solution. Okay. If B was not in the span of A, then this is something. This is not the solution because it cannot be. The problem cannot be solved. Is it clear? Or one way to verify if B is in the span of A is this. You take B, span of the column space of A is this. You take B, you multiply it by one of the left inverses. Okay, you get some vector, and you multiply it by A. And what you get back is B, then B is in the column space of A. If B is not in the column space of A and you do this, this will not be equal. Okay. Okay. Let's just verify this for this one simple example, and then we can then stop there. Okay. Let's say A, the problem that we're dealing with is this: 1, 1, x equals 2, 3. Okay. For this case, when we took a left inverse, okay, multiplied the left inverse by B, we got some x, and then when we computed A times x, we got 2.5, 2.5. So if you multiply by C on both, so if you do this, A times C times B, for some C, for any left inverse, right? The different possible left inverses are half plus alpha, half minus alpha. If you put any left inverse here, you will find that this is not equal to B. That means B is not in the column space of A, which we already knew. Okay. Now tell me what happens. If you take any left inverse, is this satisfied? What do you get when you do this? Well, you have 1, 1. This is half plus alpha, half minus alpha, multiplied by your 2, 2. Tell me what you get. Do you get 2, 2? Yeah. So that means whenever B is in the column space of A, it doesn't matter what left inverse you use, you will always solve the problem. Okay? Alright, okay. So we'll stop here. Again, the very first time you come across these things, these are probably not easy to grasp. It means you have to go back and revise the material. We'll try and upload the video by today so that you can review it before tomorrow's class. Okay. If there are any questions, we'll discuss that now. Otherwise, we'll stop here. Okay, alright, nothing. Alright, then we meet tomorrow.